Welcome back to this lecture on functions. In this fourth segment, we will consider two new properties, namely increasing functions and decreasing functions. Now, for these definitions to make sense, we must only consider numerical functions. In other words, an assumption in this segment is that both the domain and the codomain of the functions are subsets of the real numbers. So we say that a function f from D to C is increasing if and only if for any elements x and y of the domain, if y is greater than x, then f of y is greater than or equal to f of x. So an easy way to remember this definition is to picture the graph of the function in your head. What this definition says is that if y is greater than x, remember x and y are in the domain, so if you're moving toward the right on the graph of the function, what you notice is the value of the function at y is greater than or equal, that is, it's higher up in the graph than the value of the function at x. So in other words, when you move toward the right of the graph, the function is either going up or staying flat, but it's never going down. It's never decreasing. And that's why the function is called an increasing function if it has that property for every possible pair of elements x and y in the domain. And now you understand why we require the domain and the codomains to be subsets of the real numbers, or to be some kind of numbers, because otherwise we would not be able to apply the less than and less than or equal operators if they were not numbers. So, to visualize this definition, let's draw a random function. And the important thing here to understand the definition is assume that you're drawing the graph of the function with your pen going from left to right. If the function is increasing, that means at any point in time when you're moving from left to right, your pen must either go up or at worst must stay horizontal. It's always increasing or staying flat. It's never going down. So here is such a function, going up, 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 up. Oop, here you're about flat, and then you go up again. So this function, by looking at its graph, it's obvious that it's increasing. It would not be increasing if at some point in time, say from now on here, it would be going down again. That would not be an increasing function. So, this function, on the other hand, is by definition increasing. Now, the second definition is a slight modification of the first one. We say that a function f from D to C is strictly increasing if and only if for any elements x and y in the domain, whenever y is greater than x, then f of y is strictly greater than f of x. And that's the only difference in the name, strictly, and in the definition is that f of y cannot be equal to f of x. So again, graphically what this means is when you're drawing the graph of the function and you move your pen from left to right, this time you must always be going up. You can't even go horizontally. You're always strictly increasing. You're going up, and you're always going up. You're not allowed to either go horizontally or go down. Now, of course, we can define a decreasing function in a similar way, so let's do that right away. A function f from D to C is decreasing if and only if for any elements x and y in its domain, whenever y is greater than x, then f of x is greater than or equal to f of y. Notice this definition is the opposite of this one. So in particular, whenever you move towards the right of the graph, when y is greater than x, what happens is f of y is actually less than or equal to f of x. So in this case, what it means is when you move towards the right, you must either stay flat because of the equal sign here, or go down. You're not allowed to go up. So let's look at a random example here. let's say you're drawing the graph of the function from left to right, your pencil or your pen can never go up. It must either go down or stay flat, or go down or stay flat, but never ever go up. This is a decreasing function. So notice we can also impose an extra condition, namely that we don't allow these flat areas here. These are usually called plateaus, where the function is actually horizontal. And if we allow this, then the function is decreasing. If we don't allow these, then the function is strictly decreasing, and that's our next and last definition. So a function f from D to C is strictly decreasing if and only if for any two elements x and y of its domain, whenever y is greater than x, then f of y must be strictly smaller than f of x. As you might imagine, a random graph of such a function will look like this, where the graph always goes down, can never go up or even go horizontally. So whenever you're dealing with numerical functions, it's actually a good thing if you can prove that your function has one of these properties. And the reason for that is knowing that, say, a function is strictly increasing allows you to infer that this function must have other properties. Let's illustrate this with the first theorem in this lecture, Theorem 1, that states that a strictly increasing function is injective. So first of all, notice that with this theorem, we are making a connection between these definitions and the one we studied in a previous segment of this lecture. So what this theorem states is that for all functions f, if f is strictly increasing, then f is injective. So notice this is a universally quantified conditional, and we know how to prove these now. So let's use our standard direct proof technique. And the first thing we need to do is, since we are trying to prove this for any function, is we need to pick an arbitrary function. So to do that, since every function must have a domain and a codomain, we're going to assume that D and C are any subsets of the real numbers, and we're going to let f denote an arbitrary function from D to C. And then we should not forget at the end of the proof to use universal generalization to restore the for all f in the theorem. But for now, f is a specific but arbitrary numerical function from D to C. Now, the theorem we're trying to prove is a conditional. It says if f is strictly increasing, then f is injective. So we're going to write a direct proof, meaning we're going to assume the hypothesis of the conditional. In other words, assume f is strictly increasing. Now we're going to try and prove that then f must be injective. Now what's the definition of injections? Remember, a function is injective is if for all elements x and y in the domain, then if they are different elements, they can't have the same image. The point is the definition of an injection is doubly universally quantified over x and y, the elements in the domain. So again, we have a universally quantified statement to prove, so therefore we're going to pick two arbitrary elements x and y of the domain. And we don't want to forget to use universal generalization later to generalize over x and y. But from now on, we have a specific function f, and we have a specific value for x and a specific value for y in the domain. So now we have to prove that the function f is injective. So let's assume that x and y are different. Notice if x and y are equal, then we're not going to be able to infer much, because the definition of strictly increasing here has to do with y being greater than x. So if x and y are equal, we're not going to be able to infer anything about f of x and f of y other than they are equal. So let's assume that x is different from y. Now, One thing we haven't talked about yet when you're writing a proof is the ability to use this technique called without loss of generality, which means now I'm going to consider a particular case, a specific case. I assume that x is different from y, but I'm going to go further and I'm going to assume that actually y is greater than x. Now, of course, this proposition does not imply this one. It could be the case that x is greater than y. But what without loss of generality means is that it doesn't matter whether x is greater than y or y is greater than x. What we're going to do is we're going to prove the result for this case, and it should be obvious at the end of the proof that if you had assumed that y was smaller than x, you would have also reached the same conclusion. So without loss of generality is basically a shortcut that says, I'm going to do the proof in this case, and it should be obvious that it's going to hold in the other case. Make sure you check that at the end of the proof. So now we are assuming that y is greater than x. So what can we infer from that? Well, by definition of f being strictly decreasing, it must be the case, strictly increasing, it must be the case that f of y is strictly greater than f of x, since we are moving toward the right when we go from x to y. So what can we infer from this inequality? Well, then it must be the case that f of x is different from f of y. Obviously, if a number is strictly greater than another, the two numbers are different. So what did we just prove? Well, we just proved that if x is different from y, then f of x is different from f of y. By the way, now it's time to check that if we had the reverse inequality here, when we did the without loss of generality, what if x was strictly greater than y? Then clearly we would have f of x strictly greater than f of y. It would still be the case that f of x and f of y are different. So we basically covered all of the cases here. Now let's go back to our latest conclusion, which is this conditional. Well, this conditional is really close to the definition of an injection, but to get the exact definition of an injection, let's just take the contrapositive of this conditional. We know that every conditional implies its contrapositive since the two are logically equivalent. In other words, if f of x equals f of y, then it must be the case that x equals y. Now remember, x and y are arbitrary values of the domain, so now it's time to generalize over all the values in the domain. So for all x, for all y belonging to D, if f of x equals f of y, we just prove that it must be the case that x equals y. And as it turns out, this is the definition of injections. So we just proved, in other words, that f is an injective function. But remember, so far we've only proved it for one particular but arbitrary function f. So let's not forget to generalize this conclusion here we just reached using universal generalization, and to say that now for every domain D and codomain C and function f, it must be the case that if f is strictly increasing, then f is injective. And that is the end of the proof. So let's indicate this with our usual symbol. Now, to conclude this segment, I want you to think about a similar theorem that you should prove on your own, which is very similar to this one. It says, a strictly decreasing function must also be injective. So please make sure you understand this proof and that you're able to modify it to prove this slight variation of the theorem.